This next video, and this video is about defining the Gauss law. So first, in the last video, what we defined was we defined a new term known as electric flux density, and the electric flux density is given by the D and is equal to epsilon naught E for a medium like a free space. And we are now dealing with what is known as electrostatics. So this is whatever I'm saying, this video is applicable to the electrostatics. So this is the Gauss law defined for the electrostatic fields, and the next we know is that what is electric flux density is given by kq divided by r square into r square unit vector, and the unit is Newton per coulomb, and the unit of electric flux density is coulomb per meter square. And next is that if you are assuming that there is a closed surface here, and the total charge enclosed by this closed surface is q, then the flux which is coming out of this surface, that is a flux, will be always equal to the q which is enclosed. So this is a mathematical definition of Gauss law, which states that the flux enclosed in a closed surface, or the total flux coming out of a closed surface, is equal to the charge which is enclosed or which is present in that surface, assuming this is a three-dimensional closed surface which you are having. So you can say that your q, if you are considering this, the charge, this is a three-dimensional surface and this is a volume of charge, and the charge per unit volume is equal to rho v. So rho v is equal to charge per meter cube. So that is the charge per meter cube, and your q will be equal to the integration of rho v dv, that is equal to the total charge present in that area. So you're doing a volume integration. So again, the dv is equal to meter cube, and when you're multiplying it by charge per meter cube, what you will be getting is a charge, and when you are integrating it of the whole volume, you will be getting what is a charge q. So that's how you have got this here. And now when you are having it, when you are applying the divergence theorem, what it said was the divergence theorem, not divergence theorem, the electric flux density. So what the electric flux density said was that the D is equal to, or the equation of the flux was D integration of surface integration of D dot ds, which is equal to the total flux, so in any surface. So if we are putting that here, so what you will be getting is that the flux is equal to integration D dot ds, which is equal to q by Gauss law. So this is the first equation, this is the second equation which you got, this is the third equation which I have, and based on these three equations, it's possible to say that, and this is what we are doing, the Gauss law, first defining it and defining the Maxwell's first equation for electrostatic fields. So this is deriving the Maxwell's first equation. So D dot ds is equal to integration v rho v dv. So based on the 1, 2 and 3, we can write this. So substituting the flux here, So this is what you are getting. So this is my fourth equation. Now if I am applying the divergence theorem to this equation, so the divergence theorem, which is my fifth equation, if I write, says that the surface integral of a vector over a surface is equal to the divergence of that vector or the volume integral of the divergence of that vector over that volume. So this was my divergence theorem, and now simply you are saying this is your divergence theorem, and now you have to apply your divergence theorem here. So this is my fifth equation in this case. So now when I am applying the fifth equation on this, what I will be getting is I can apply the divergence theorem on this side, which will make my equation is in both the equation in form of volume integral, and it will say that the divergence of my vector d, or divergence of electric flux density over a volume dv, equal to the volume integral of the volume charge density. So based on that, I can say that the volume charge density, so this is my sixth equation which I have got. So based on the sixth equation, I can say that the volume charge density, which is this part, is equal to the divergence of my electric flux density. So this statement that the volume charge density in an electrostatic field, which we are considering here, is equal to the divergence of the electric flux density, is known as the Maxwell's first equation, which can be stated as rho dot d, or del dot d, which is a divergence of electric flux density, equal to what is known as my electric charge density. So this is Maxwell's first equation.